So now that we've talked about energy and power and efficiency and sources of energy, we're going to focus on two other sources of energy a bit more in depth. One of them being thermal energy, the other being nuclear energy. So the next few lectures are going to focus on thermal energy. This one talking a bit about thermal energy and heat. So we're surrounded by the use and effects of heat and thermal energy. So at home, your home's temperature is controlled by a thermostat, which controls the furnace or the air conditioner. Large bodies of water help moderate the climate of certain regions. Winds are generated by the uneven heating of the Earth's surface and atmosphere when basically the air in one region ends up moving to another. And that's what causes wind, and that happens because of changes in temperature. And lastly, it says here the weather influences the clothes that we wear. Furthermore, much of the energy we consume is eventually transformed into thermal energy. A lot of the food that you eat, that chemical energy for the food, is turned into thermal energy to heat your body. Thermal energy is the total kinetic energy and potential energy of the atoms or molecules of a substance. It depends on the mass, temperature, nature, and state of the substance. Heat is the transfer of thermal energy. So thermal energy, the definition is the total kinetic and potential energy possessed by the particles of a substance. So now let's think about this a bit differently. What do we mean when we're talking about the kinetic and potential energy possessed by the particles of a substance? Well, you would recognize that from the particle theory, all objects are a series of particles. And those particles could be molecules, for example. Something that has a lot of thermal energy has a lot of movement between its molecules. And as it moves, the molecules will collide with each other and have friction reactions, and those little friction reactions will cause heat to be generated. Will cause the thermal energy to increase. So when we're talking about the total kinetic and potential energy of a substance, thermal energy is how much energy the particles in a substance have based on their movement and how much energy they can have based on their composition. So when we refer to temperature, what we're actually talking about is the average kinetic energy of the particles in a substance. So when you are out, if you're outside on a nice day and it's 30 degrees Celsius, that temperature is the average kinetic energy that the particles in the air have as they touch your skin. So if we increase the motion of those particles, we have greater temperature. So for example, on a cold day, the particles in the air aren't moving as much. So there's less interaction with your skin, less friction reactions with your skin. On a hot day, we have those air particles moving a lot faster. They touch your skin and they have these friction reactions which end up warming your body. Let's consider two water sources here. 100 grams of water at 50 degrees Celsius and 500 grams of water at 50 degrees Celsius. These samples have the same temperature, but the bigger 500 gram sample contains more thermal energy because it has a greater mass. If you mix these samples together, there is no transfer between the two because they're at the same temperature already. But let's consider if we have 500 grams of water, that's 50 degrees Celsius, and 500 grams of water, that's 90 degrees Celsius. Well, the 90 degrees Celsius water has more thermal energy, and when we mix them, their there's going to be a transfer of energy from the 90 Celsius water to the 50 Celsius water. And it'll end up where the temperature of the mixture will be somewhere between 50 degrees Celsius and 90 degrees Celsius. But we'll have to do some mathematics to determine what the actual number would be. So this practice question says we have a parent placing a baby bottle containing 150 milliliters of milk at 7 degrees Celsius into a pot containing 550 milliliters of water at 85 degrees Celsius. So let's compare the average kinetic energy of the milk and the water. Well, the water has the greater temperature than the milk. So we would have more thermal energy in that water than in the milk. Sorry, I guess the next question. Compare the thermal energy. Well, the water has more thermal energy than the milk because it's hotter and there is more of it. What about, it says, when will the thermal energy stop transferring? And it will stop transferring when the milk and the water reach the same temperature. So this is something that parents typically do to heat up milk that is colder. They put it in a source of water that is warm, and eventually the milk will warm up. So there are 3 ways that heat is transferred. And this picture of a campfire actually gives the 3 of them. Let's say we have a campfire and you have a metal poker and you put that into the fire. Well, the poker itself will warm up and heat will conduct through that metal poker. Putting your hands above the fire, the fire will heat the air, and the heat will the thermal energy will transfer through the air and heat your hands through convection. And radiation, you don't necessarily have to have your hands on top of the fire, but being near the fire, you can warm your hands. What's actually happening there is the fire itself is causing light. Light is caused by the movement of particles called photons. And the photon is the transmitter of the electromagnetic force that radiates from the fire to your hands, and then it has an interaction, a photon interaction with your hands to warm them up. So that's radiation. And we'll go through each of these a bit more. First, conduction. So this is when we have fast moving particles next to slower moving particles. Just being in contact, the slower moving particles will start to move faster, and that's how we would heat the something that has slower moving particles. So the heat conducts through the metal usually to warm it all up by speeding up the particles that are inside of it. So conduction is a transfer of thermal energy from a warmer object to a colder object. It occurs through the collision of atoms. You might have had a metal spoon inside of a hot beverage like a tea. That's another example of conduction. So eventually the spoon inside the tea will have a lot of interactions with the moving particles in the tea. That will heat up the metal on the end of the spoon, and then that will start to spread out to the tip of the spoon. Convection is how thermal energy is transferred in a fluid, and it could be a liquid or a gas. Looking at the pot on a stove, this is kind of an idea that makes it a little bit easier to understand. The first water to be warmed will be the water at the bottom of the pot. Warmer water tends to move up, or even warmer air. All warmer fluids move up. So that warm water will move up, and as it moves to the top, it will displace that colder water. The colder water will sink, it'll move down, it will be heated up, and then it will rise to the top. And that water at the top will then be colder than the water at the bottom, so it will move down, and we have this cycle of convection. That's where you see the rolling boil sometimes. In a home heating system, you'll typically see vents at the bottom of the floor so that they can heat the bottom, the air at the bottom, which will then rise up, and then it'll create a convection current. The air will flow through the area, so we'll have the warm air rise up, the cold air move down, the cold air will be warmed, and then rise up, and then as it cools down, it rises down. So we have this this cycle. That is convection, and this is the concept of a convection current. This happens in on Earth as well, right? We have warm air gets warmed on the land. It tends to go over the sea where it cools down, and then it goes down towards the sea level, and then we have a cycle. This is why the air off of a water body typically is colder, because it's the end of the convection cycle outside. And then lastly, we have radiation. So thermal energy also is transferred by radiation. Radiation is a thermal energy transfer that involves electromagnetic waves being emitted from sources such as lamps, flames, and the sun. While the sun is the largest source of radiant energy, all particles that have kinetic energy emit some radiant energy. You yourself are actually a source of radiant energy. Your heat, the heat that's coming off of your body is being radiated out, and this is why a thermal imaging camera will show any living things as having a heat signature. So write down these notes for radiation. It's a transfer of thermal energy as electromagnetic waves. Does not require the collision or movement of particles. So you might wonder how a thermometer works. When we place a thermometer in a liquid, the liquid, the particles, the molecules in the liquid will hit the glass of the thermometer. That will eventually get to the material, the mercury or the colored alcohol in the thermometer, and as that vibrates faster, that mercury will end up kind of expanding. Its expansion is limited by the shape of the container it's in. So because it's a long tube, and the thermometer is it will be calibrated to the indentations on it, you would see the mercury or the colored alcohol rise to a certain point, and then you can indicate what the temperature is just by reading off of the thermometer. This here is going to explain that even further, so you can read that on your own. So thermal energy can also be insulated. So sometimes we want things to be warm and sometimes we don't. So there are things that are conductors. Thermal conductors are usually metals. That's something that heats easily. Also, the idea that a metal is a thermal conductor also means that it will lose thermal energy quickly. So this is why a metal sometimes feels cold, because it doesn't have a good ability to retain that thermal energy. But we have thermal insulators as well. These would be materials that prevent heat, so they prevent the transfer of thermal energy. You might notice that some pots and pans have handles made of a different material That's so that the handle doesn't get warm. Here it says the best thermal insulator of all is a vacuum. A vacuum is a region of space that has very few particles in it. And a perfect vacuum has no particles. Well, if we have no particles inside of a vacuum, we have no molecules to hold thermal energy, to have kinetic interactions, we would then have a perfect insulator, because we wouldn't have the ability to move for particles to interact with faster moving particles. This is the concept of a thermos bottle, where it has an inner flask and an outer flask, and then there's a little vacuum. So this would make your hot foods hot and your cold foods cold. Discuss whether this statement is true or false. In conduction, thermal energy is transferred by the particles themselves. Thermal energy is transferred, but the particles themselves are not transferred. This is true. When we have conduction, materials have to be in contact with each other, but they could be two different types of molecules. The particles don't move to another material. They interact with the particles at the edges of that material, and then those particles interact with the other particles within that material. So it transfers, the energy transfers. So is air a good conductor? That's the question. So, and if air was a good conductor, then you would feel cool even on a day when it's 25 degrees Celsius outside. So if that was the case, if air was a good conductor, you would always be heating the air just by being outside. So your 38 degrees Celsius, as you were outside, you'd be losing thermal energy to the environment, to the air, to heat up the air. So if that would be the case if air was a good conductor, which it's not. Here's another question to consider. Would it be better to place an electric room heater near the floor or the ceiling of a room? Well, we have to use the idea of convection. And if we're near the floor, we could heat the air at the bottom of the floor. It would then rise up and dispel cooler air at the top. And then we would heat that cooler air that was at the top. It would rise up, and we would have a convection current. If you were heating at the top, you'd already be heating the warm air, and that warm air would stay at the top, so you would just be overheating that warm air, and it won't circulate as much.